Another algebraic method used to solve systems of equations is called the method of elimination. And elimination is sometimes referred to as the method of addition because we end up adding the equations in this process. Let's take an example. Suppose we have these two equations in our system of equations. The concept here in this method of elimination is to manipulate one or both equations so that the coefficients of the x terms or the coefficients of the y terms are identical except for sign. And we can easily accomplish that kind of pattern here by, well, we can sort of attack the coefficients of x or the coefficients of y. If I attack the coefficients of x, here's what I would think. I would think, well, in order to cause the coefficients of x to be the same except for sign, I can multiply in equation 2 by 3. Now, I'll first bring down equation 1. I'll write minus 3x plus y equals negative 2, and then I'm electing to multiply through equation 2 by 3. So 3 times every term. So 3 times x, 3x, 3 times 2y, 6y, 3 times 10, 30. Now I'll add the two equations. Hence the idea of addition for this method. Well, adding the two equations, the terms involving x will go out as expected, then 1y plus 6y, 7y, and on the right, negative 2 with 30, 28. Dividing on both sides by 7, we find y to be 4. Now that we have the value of y, we back substitute in order to find the value for x. So we'll back substitute into either of the original equations. Now, unlike the method of substitution, remember, we don't have a convenient equation in which to do the back substitution. So we have to back substitute into one of these. And it doesn't matter which one. I'm going to use equation 2. Equation 2 is this. And we found y to be 4. So I have x plus 2 times 4. X plus 8 is 10. X then is 10 minus 8. X then is 2. So the ordered pair 2, 4 solves the system. Now you may recognize this system of equations as a system that we had earlier. That is, we solved this same system by substitution in an earlier segment. So we're seeing two different ways, two different styles for solution in the same system. And I think by rewinding the tape, maybe looking at the previous section, you can see the distinct differences in the two methods of solving. Now remember, the concept here is to look at the coefficients of the x's, look at the coefficients of the y's, select one pair of those coefficients to attack, try to make the coefficients differ by sign only. And then you can add the equations and that particular letter will go out of the system. Now do understand that with this method of elimination that we are conceptually performing the same kind of attack on the system of equations. That is, we're taking a system of two equations and two unknowns and we're reducing it by this elimination idea to a system of one equation in one unknown and then solving that equation and then back substituting. Let's go through the process again. Here's another system. Now, I can elect, as I said, to attack the coefficients of x or the coefficients of y. And sometimes one of those pairs is easier to deal with than the other. If I were to attack the coefficients of x, then I would end up having to manipulate in both equations. Now, I know that the least common multiple for 2 and 3 would be 6. So I'd have to multiply in equation 1 by 3 and in equation 2 by 2 in order to accomplish 6 as the coefficients of x. And then I would have to, at the same time, I would have to multiply in one of them by a negative value in order to have that sign difference. Well, that means quite a bit of manipulation if I'm going to attack the coefficients of x. So I'll elect to attack the coefficients of y because I only need to multiply in equation 2 by 3. So equation 1, equation 2. I'll bring down equation 1. In equation 2, I'm electing to multiply by 3. 3 times 3x, 9x. 3 times y, 3y. 3 times minus 5 minus 15. Adding the two equations, let's see, 2x and 9x, 11x. The y terms go out as expected. On the right, negative 7 with negative 15, negative 22. Dividing on both sides by 11. That's ugly. How about this? We find x to be negative 2. And again, we substitute back into one of the originals to find the value of y. I think it's a little easier to pop that value into equation 2. Let's come over here and do that. So let's see, x is negative 2. We have 3 times negative 2 then, plus y equals negative 5. This is negative 6. Add 6 on both sides. So y is 1. And the ordered pair then, negative 2, 1, will solve the system. Another example. In this one, as I look at the coefficients of the x's and y's, it kind of looks like attacking the coefficients of y would be a little bit easier. The coefficients are smaller, and we only have to multiply in one equation. Here we would only have to multiply in one equation also, but the numbers are a little bigger. So, looks like it's a little easier to just multiply in equation 1 by 2. So in equation 1, I'm multiplying by 2. 2 times negative 4x, negative 8x. 2 times y, 2y. Whoops, negative 8x plus 2y. 2 times 3, 6. Bring down equation 2. And add the two equations. Minus 8x plus 8x, 0x. That term goes out. 2y minus 2y, that term goes out. The only thing left on the left side then, when we add the two equations, is 0. And on the right, we have 6 minus 8, that's negative 2. So all of the letters disappeared from the equation, from the system of equations once we're manipulated this way. And that's the tip-off that says something funny's going on here. Either we have a system of equations that has no solutions, or we have a system that has an infinite number of solutions. We have a dependent system, or we have an inconsistent system. Now, since the resulting statement of equality is false, that tells us that we have no solutions to this system of equations, and therefore the system is an inconsistent system. No solution. Now, graphically, we know that this situation would manifest itself in graphs that are parallel. So the lines would be parallel, never intersect, therefore no solution. As you might imagine, many word problems lend themselves to a solution using systems of equations. Now, those problems, a lot of times you can be tipped off as to the idea of using a system of equations when two unknowns are requested in the problem. Problem like this. 500 tickets were sold to some event, let's say, some school event. $3,312.50 was collected. The adult tickets were $7.50 apiece. Children's tickets were $4 apiece. How many tickets of each type were sold? How many tickets of each of two types, you see, were sold? Ding, ding. We might have a way of solving this using a system of equations. Now, so we're going to just represent the unknown quantities here with x and y. But I want you to realize that this problem can be done using some of the techniques we've already learned about. And in fact, some of the problems that we have solved in the past can be solved by using a system of equations. A lot of times you see variables have been represented in terms of one another. That is, unknown quantities have been represented in terms of one another. And that's the technique that we have had to take in all of the problems in the past. For example, on this problem, we could represent the number of, let's say, adult tickets as x. Well, then we could represent the number of children's tickets as total number of tickets minus x. You see, that could be a representation for the number of children's tickets. Well, we're going to take a different tactic here, though. We're going to just say, well, we have two unknown quantities. Let's just do this. Let's just let x let x equal the number of adult tickets. And let's let y equal the number of children's tickets. Okay, that's the start. Now we'd like to build a couple of equations using those two letters, using those two unknown quantities. Sometimes in this situation, the first equation is rather trivial. You want to look for a relationship involving x and y. You want to look for an equation where you can just add, subtract, multiply, or divide the x and y that's involved in your problem. A lot of times some kind of equation will emerge. Now here, for example, x is the number of adult tickets, y the number of children's tickets. Do we know the sum of the numbers of tickets? Well, yes, we do. Right up here it says 500 total tickets were sold. So one of the equations is relatively trivial. It is simply x plus y equals 500. Now the trick is to form another equation using the given information. And the rest of the information involves money. So chances are we're going to have an equation that involves the total amount of money. And that certainly is the case here, that we can represent the amount of money collected in adult tickets by multiplying the number of adult tickets times the price of one ticket. And the total value of the children's tickets would be $4 times the number of children's tickets, you see. And then the sum of the value of the adult tickets plus the value of the children's tickets will give the total amount of value for all of those tickets. So that's the concept for building the second equation. Here are the two equations. Equation 1 is simply x plus y is 500. Number of adult tickets plus the number of children's tickets is 500. So that's equation 1. Equation 2 addresses the idea of value. This is the value of the adult tickets. This is the value of the children's tickets. All together we have the total value of all tickets. So we're using a lot of the concepts that we talked about before, but we're putting it together into this structure of a system of equations. All right, now it's a matter of going through and solving. I think the hardest part, or the part that we want to emphasize the most, though, has already been discussed here. And that's true for all of the problems that you're going to work in this environment. The answers are not nearly as important as the setting up of the problems correctly, the building of the equations from the information given in the problem. If you're able to do that, whether you get the answers right or not, you are successful with these problems. All right, just for completeness, though, let's go through and solve the system. Now, I'm going to use the method of elimination here, so I'm looking at the coefficients of x, I'm looking at the coefficients of y. I think I will attack the coefficients of y. I'll make this coefficient a -4 by multiplying through this equation by -4. -4 times x, -4x, -4 times y, -4y, -4 times 500, -2000. All right, then I can add the two equations. The y terms go out as expected. -4 with 7.5x is 3.5x. Then collecting here, we get 131250. And then dividing on both sides by 3.5, we find x to be 375. Now, x stood for the number of adult tickets, so we label this as 375 adult tickets were sold. Now, there's a tendency for students solving problems like this to stop at about this point, where when they find x, when a student finds x, they think, I'm finished. Well, that may have been true in previous problems, but it's not true here. We had two things we were looking for in the problem, and so we have to identify the other unknown quantity, and that's the number of children's tickets in this case. But as a matter of form, as you go through and solve problems, word problems of any type, it's wise when you think that you have an answer to go back to the original problem and read the question that is being posed. Are you answering the question being posed? And that will save you a lot of grief and a lot of careless mistakes in problems like this. Okay, so we want the y value now, so to find that y value we go back to the original set of equations, we find that equation 1 is a good deal easier to deal with than equation 2. So we use equation 1 and put this information about x into it. If x is 375, we replace x with 375 and solve for y. To do that, we'll subtract 375 on both sides to find that y is 125, and that's 125 children's tickets sold. Here's another problem. This one involves distance. And once again, it may be possible for us to use another method to solve this one, but I think it'll be pretty clear as we get into this problem that it's a lot easier to solve it using a system of equations. In this problem, we have two directions of travel. We have one vehicle, but two directions of travel. Let's say we have a motorboat, and the motorboat travels upstream 18 miles and downstream 18 miles. So we're coming back to where we started. And let's say the little motor is running flat out. Just as fast as it can go, it's the same motor speed going upstream and downstream. Okay, now that doesn't mean that the boat is traveling at the same speed, because there's a current. Okay, now let's say that the trip upstream takes 1.5 hours, but the trip downstream takes 1 hour. And we want to find the speed of the current. Okay, speed of the current. Now, there are two speeds that are unknown to us here. And in fact, the problem could be requesting the boat speed in still water as well as the current speed. But the problem is only asking for the speed of the current. All right, but we're going to need that boat speed in order to figure the speed of the current. So we can interpret here that there are two unknown values here. Now notice that we're not directly requesting two unknown quantities, but we can interpret it as requesting two unknown quantities, and that then is a tip-off that we might use a system of equations. I know it's a little bit of a reach at this point, but when you get a little experience with this, you'll learn to trigger that idea of when you have systems of equations that can be used on a problem and when you don't. Okay, so boat speed, current speed, that's the two unknown quantities. So we might let x be the boat speed in still water and y be the speed of the current. You can switch the letters around if you want to. It really doesn't make too much difference. All right, then away we go with trying to build equations involving this idea. Now, I mentioned in the previous problem that one thing you might investigate is the idea of x plus y or x minus y or something like that, just something involving the x and the y. Do we have any kind of relationship here involving the boat speed and the current speed? Do we have the difference? Do we have the sum? Anything like that? No, we really don't. Okay, we can't use that technique. So what do? Well, we resort to the stuff that we learned before, and that is when we had either two vehicles or two directions of travel involved in a problem, we set up a table of information, and the table would look like this. Now we have information about upstream and downstream travel. We have distance, rate, and time, and we just go through and try to fill in the information that we know. And it's a pretty trivial situation to write down the upstream distance and the downstream distance, because it was 18 miles upstream, 18 miles downstream. All right, so 18s go here. The time also is relatively trivial to put in terms of the given information. We were told that the upstream time was 1.5 hours, the downstream time was 1 hour. All right, so that's easy. Now, the trick here is to write in the rate going upstream and downstream. And it's important to realize that going upstream, the boat is having to push against the stream. The boat can't go as fast as it ordinarily would. So we have a boat speed in still water minus the speed of the current. You see, and then going downstream, it's like, whoa, the current is helping the boat go along. And so it's a plus idea. It's the addition of the boat speed plus the current speed. So going upstream, it's the boat speed minus the current, and going downstream, it's the boat speed plus the current as the rate. All right, now with that information, we pretty much have our two equations built in here, because we know that distance is rate times time. We have distance, rate, and time for each of these directions of travel. So let's see, distance is rate times time. The distance, 18. Rate is x minus y going upstream. The time is 1.5. And going in the other direction, It's 18 for distance, x plus y for rate, and 1 for time. And now it's just a matter of massaging this a little bit and getting an answer. Well, the tough part of the problem is up to this point where we build our two equations. We're going to go ahead and finish this problem, but I do want you to know that there are other ways to deal with this, other ways to solve this. You might look at the solution in your textbook. This is one of the ones that is an example in your text, and I invite you to look at it because it's a method of solution that's a little bit different than this. But the more you know about a variety of ways to solve even the same problem, the better off you're going to be in dealing with them on your own. Okay, to finish out the solution here, x minus y times 1.5. 1.5 times x is 1.5x. 1.5 times minus y is minus 1.5y. And then in the other equation, 1 times each of these just gives us x plus y. Now we look at this system of equations, and if we're going to use the method of elimination, which is what I'm using here, then I would attack the coefficients of x or the coefficients of y. I notice that I have a sign difference here for the y, so I will attack there. I'm going to multiply in equation 2 by 1.5. So I bring down equation 1, and then 1.5 times 18 is 27. 1.5 times x, 1.5x. 1.5 times y, 1.5y. Add the two equations, 18 and 27, 45. 1.5 and 1.5, that's 3x. And the y terms go out as expected. Now I have 45 is 3x. Let's come up here and continue. We have 45 is 3x, dividing on both sides by 3, we find x to be 15. Now x was 15 miles per hour. It was the speed of something. It's important to write down what we're using for x. That is, what does x represent? It's important to write that down somewhere, as we did over here. We said let x equal the speed of the boat. Because you see, if you don't write it down, then how will you know what you have here for this value? You see, and if you get confused about what this stood for, you can go back and look at where you wrote it down and say, oh yeah, it's a boat speed. Okay, so it's 15 miles per hour is x, but x stood for the speed of the boat. Is that what we are looking for in the problem? No! We weren't looking for the boat speed. Didn't ask us for the boat speed, it asked for the current speed. But we can easily find that value by using one of the original equations, and this is the easier one, I think, and put in this information for x. So we let x be, or replace x with 15, subtract 15 on both sides, we find y to be 3, and that's 3 miles per hour, and that stood for the speed of the current.